So in this subpart of the third lecture, we will discuss two applications of the calculus of variations. The first one is very basic yet very interesting, that is to find the shortest distance between 2 points in a plane. Okay, so let's say we are fixing 2 points A and B, and we can assume several type of paths joining A and B, and we have to see, or rather we have to find out which curve of this can give us the shortest distance between A and B. Now, how to define the distance at all? So an elementary distance along any arbitrary curve is given by ds, which is equal to root over dx square plus dy square, because this is 2D plane, of course. And then along any curve C, the distance between the points A and B will simply be an integration along this curve C of ds. Right? So we can just then expand this ds as root over dx square plus dy square along C, and then we just take dx out of the root over, and we can just write this one as some root over 1 plus dy dx whole square times dx. Now you can see that if we think this SC to be equivalent to j, and this is equivalent to f dx, then this part is nothing but this function f, right? Something like that. Okay. So if the path for which the distance is minimum is C, then for that, if the corresponding function is f, then we know f must satisfy this relation that we have proved. Okay. Now here our f is this, so we know this should be true. Clearly, we can then calculate del f del y dot and del f del y. Now you can see that f only contains here y dot and no y is there, so del f del y is 0. But del f del y dot is nothing but y dot by root over 1 plus y dot square. Okay. So finally, this condition gives us that ddx of y dot by root over 1 plus y dot square is equal to 0. If you do some lines of algebra, very simple algebra, you will see this is nothing but y double dot by root over y dot square minus half y dot dot 2y dot y double dot by 1 plus y dot square to the power 3 half. Then you can take common the factor of y double dot by root over 1 plus y dot square, and then you divide the whole thing by this factor, and finally you will be left with this 1 minus y dot square by 1 plus y dot square, which is equal to 0, and it simply gives you y dot square is equal to 1 plus y dot square. And what is that? You will have 1 is equal to 0, a new proof of 1 is equal to 0. Well, we all know that this is wrong. This is mathematically impossible, right? So what is the reason for that? It is simply because we have divided the whole thing by y double dot over root over 1 plus y dot square, assuming that to be non-zero, and that actually is 0 in this case. As this is 0, then we can simply say y double dot is equal to 0, and y is nothing but a linear function of x, can be written as y is equal to ax plus b. Another way of doing this is, if this is 0, then we can easily say y dot by root over 1 plus y dot squared is equal to 0. Sorry, this is equal to constant. Okay. And if this is equal to constant, we are taking the square of this, and we can say that y dot square by 1 plus y dot square is also constant, and from that anyone can show that y dot square is also a constant and y dot is a constant, which is again the equation of a straight line. So we are done. Now coming to the second problem. The second problem is known as the problem of brachistochrone. The brachistochrone has a Greek origin, which simply means the shortest time. The statement of the problem is, if a point particle is falling from rest under the influence of gravity from a higher point to a lower one, need not be on the same vertical line. For example, it starts from 1 and it reaches 2, right? Then which curve between those 2 points should the particle follow so that this corresponds to the least or shortest time? Okay. So for that we have to minimize which quantity? The time. Then we have to write the total time spent between 1 and 2 is nothing but integration from 1 to 2 dt, but always along the curve. That we have to always remember. Now that dt can be written as ds along the curve, of course, by v, the velocity at that point. Okay. Now ds we can again write, as this is also a problem of 2D plane. You can think that the plane where like the direction which is like vertically outward, which is outward or inward of the plane of the paper, is not really playing any role. So any motion of the particle is only considered in the plane of the paper. Okay. Then you can simply say ds is also equal to root over dx square plus dy square. What is v? V we can calculate from the conservation of energy. Now we can assume this line as the reference of potential, and we can also, by using usual convention, we can say our y is negative downwards. So we can say at this point 1, the total energy, kinetic energy is 0 because it was at rest, and potential energy is 0 because it was as a reference of potential. Then at P, let's say some intermediate point, it has a kinetic energy half mv square, but potential energy minus mgy, where the y is minus y is the coordinate of P, y coordinate of P. Okay. Then simply by using energy conservation, you can write half mv square minus mgy is equal to 0, and v is equal to root over 2gy, where y is greater than 0. Okay. So then you can simply replace the value of v here, and you can have again something like f dx, right? Where f is now root over 1 plus dy dx square over root over 2gy, right? Now your f contains both y dot and y. Okay. And in order that the time should be minimized, this function f should satisfy this equation once again. Now you can simply calculate those two differential coefficients, partial differential coefficients. Del f del y dot is y dot by root over 2gy times root over 1 plus y dot square, and del f del y is equal to minus half root over 1 plus y dot square by root over 2g times y to the 3 half. Okay. Now for the correct curve, that means if to give you really the brachistochrone or the minimum time, okay, you have to follow this equation. Well, this can frighten some of you, but if you really do with patience, finally you are left with very elegant form like this. Y double dot by 1 plus y dot square is equal to minus 1 by 2y. Please check this at home. Every calculation what I am presenting to you, you are really suggested to do that at home on your own. Okay. And if you just proceed in this way, you can finally see that this is nothing but 2y double dot plus y dot square plus 1 is equal to 0. And voila, that is very elegant. Now it can be actually much more interesting if you find something so that you can make the whole thing an exact differential. The trick is to multiply the whole thing, this thing, by y dot. If you do that, the first two terms will be combined to give you ddx of y dot square, and this one is nothing but dy dx. So finally you can easily write this is ddx of y plus y dot square is equal to 0, and this quantity is constant, right? Then y dot is equal to root over c minus y by y. Now you guys know much better than me that a very good substitution, trigonometric substitution to solve this type of problem is that y is equal to c sine square t. If you replace that, you will have this equal to this one, root over integration root over y by c minus y times dy will be equal to ct minus c by 2 sine 2t, and this is nothing but x. Okay, of course there will be another d which comes because of the constant of integration. Okay, now if you just suppose that at t is equal to 0, x was also 0, then you can forget about d, and you can say that my curve is giving simply x is equal to ct minus c by 2 sine 2t, and as I myself substituted y is equal to c sine square t, and I know that sine square t is nothing but half times 1 minus cos 2t, then I have this parametric curve. X of t is given by ct minus c by 2 sine 2t, and this is c by 2 minus c by 2 cos 2t. This is the famous curve which is known as cycloid. It will give you the part of cycloid between those two fixed points. Okay. So basically you see that although if I give you these three curves and you don't know about this Brachistochrone problem in advance, your first temptation will be to choose that, sir, among this path AOB and this curved path, this will be the path of shortest time, and that's wrong. This will be the path for shortest time. Okay. In the discussion session, I will show you in some video or something. Okay, really it is the fact. Okay, historically this problem was the problem which led John Bernoulli, one of the forefathers of hydrodynamics, to the formal foundation of the calculus of variations. So he was the founder of calculus of variation, which we learned today. Okay, so that was all about this mathematical technique and its application. From next week we start the formal Lagrangian mechanics. Thank you very much.